So in this example, we're asked to show that if the collection of vectors u, v, and w is an orthogonal set of non-zero vectors in Rn, then this set must be a linearly independent set. Okay. So in order to show this, we need to think about the definition of linear independence, which hinges on solutions to the equation c1 times the first vector plus c2 times the second vector, c3 times the third equals the zero vector, that this equation has only the trivial solution. I'm going to put arrows above my vectors to distinguish them from the scalar quantities here. So let's start with suppose that we've got this linear combination of the vectors within this set equal to the zero vector. Then again, if we want to show that this is a linearly independent set, we want to show that this equation has only the trivial solution. Okay, so here's the trick to this. Take the dot product or the inner product of both sides of this equation with the first vector here, u. So take the inner product. We're going to do c1 times u plus c2 times v plus c3 times w. So this side, dot product with the first vector u equals the zero vector, dot product with u. But the zero vector, dot product with any other vector, if all of the entries of the zero vector are 0, you multiply times the corresponding entry of u, take the sum, that's always going to be 0. The scalar quantity 0 here. On this side, you can distribute the inner product of u times each part of this linear combination here. So we can write c1 times u dot product with u plus c2 times v dot product with u plus c3 times the inner product w with u. Okay, equals the scalar quantity 0. Now, since this set is orthogonal, that means that u is orthogonal to v, so this inner product must be 0. And u would be orthogonal to w, so this inner product must be 0. Also, so since u, v, and w are all non-zero vectors, u is not the zero vector, which means this quantity right here is strictly greater than 0. It's going to be some positive quantity. The important thing for my purposes right now is that it's not 0. So u dot u is not 0. These other inner products are 0. So I can write, all right, then c1 times u dot u must equal 0, since the other parts of this sum are 0, which means c1 is equal to 0 divided by u dot u. And I can do this because I know that u is a non-zero vector, so I'm not dividing by 0 here, which means c1 is equal to 0. Now, I'm going to do some erasing. I'm going to do this maybe the sort of lazy way. But note that, okay, so if we started over with this, so go back to this equation, but this time take the dot product with the second vector, let's say v. So I'm going to erase. We would write the exact same thing, but take the inner product with v. And I need my erasing rag here because my dry erase board eraser has been used up. Okay, but so we're going to go through the same process, but this time take the dot product with v. So still you have the zero vector dot product with any other vector. This is going to be 0. So now you distribute the inner product with v. So u times, or u inner product with v, and then v dot v, and then w dot v. And now u dot v, this is 0. Because the u, v, w is an orthogonal set. So u is orthogonal to v. W is orthogonal to v. This is 0. And this is not 0. because V is a non-zero vector. So we have C2 times V dot V is equal to 0, which if you divide both sides by V dot V this time, then we have C2 equals 0. So now we have C1 must equal 0, C2 must equal 0. Well then, since W is some non-zero vector, we already have that C1 and C2 must be 0, which means we've got a multiple of a non-zero vector here equal to 0. Well, then C3 is going to have to equal 0 as well. And so since our only solution, we've proven now, is where C1, C2, and C3 are all equal to 0, then we have only the trivial solution to this equation. And so that proves that the set UVW is a linearly independent set. And so we can form this conclusion of when we have a finite set of orthogonal, non-zero orthogonal vectors here, then we can assume that that's a linearly independent set.